In this section, we explain how to calculate the reaction forces. When several vertical action forces act on a cantilever beam. A cantilever beam is a statically determinate structure with 3 reaction forces and no intermediate hinges. Therefore, all reaction forces can be determined using the equilibrium conditions in 3 directions. For an object at rest, equilibrium in all directions must be satisfied. The cantilever beam, we will discuss, has a fixed support at point A, a free end at point B, and a length of L, as shown in the figure. We will determine the reaction forces when the vertical action forces P1, P2, and P3 act at the points indicated in the figure. Steps for determining reaction forces. Step 1. Create a free body diagram of the reaction forces. Step 2. Determine all the reaction forces by applying force equilibrium in the 3 directions. Step 1. Create a free body diagram of the reaction forces. For a beam, a free end allows movement in all directions, vertical, horizontal, and rotational. A roller support allows the beam to move freely in the horizontal and rotational directions, but restricts movement in the vertical direction. A hinge support allows the beam to rotate freely, but restricts movement in both the vertical and horizontal directions. A fixed support restricts movement of the beam in all directions, vertical, horizontal, and rotational. The fixed support at point A restrains vertical, horizontal, and rotational movements of the beam, so the reaction forces at point A are the vertical reaction force VA, which restrains vertical movement, the horizontal reaction force HA, which restrains horizontal movement, and the reaction moment MA, which restrains rotational movement. The free end, at point B, allows for movement in all directions, so there are no reaction forces acting in any direction. The directions of the reaction forces are assumed as follows. VA is upward, HA is rightward, and MA is counterclockwise, as shown in the figure. Note that the symbol for the reaction moment, shown in the free body diagram, uses the same notation, M, as the action moment. Therefore, it is necessary to analyze whether the M symbol in the free body diagram represents the action moment or the reaction moment, and to proceed with the analysis of force equilibrium and other related analyses accordingly. Step 2. Determine all the reaction forces by applying force equilibrium in the 3 directions. The unit of a moment is not Newton, but Newton meter. Therefore, the moment m cannot be summed with the translational forces with the unit of Newton. A moment is a quantity that does not need to be considered in the equilibrium of translational forces. In other words, a moment does not affect translational motion, but only affects its rotational motion. We will now analyze the equilibrium of forces in the vertical direction. Refer to the free body diagram of the reaction forces for the vertical forces. The vertical forces are VA at point A, P1 at point C, P2 at point D, and P3 at point B. We will derive the equilibrium equation for these forces. In the vertical force summation, forces acting upward are considered positive. Let's clarify this. The force VA acts upward, so it contributes plus VA. The force P1 acts downward, so it contributes minus P1. The force P2 acts downward, so it contributes minus P2. The force P3 acts downward, so it contributes minus P3. To achieve equilibrium of these vertical forces, the algebraic sum must be 0. This concludes the discussion on vertical forces. We will now analyze the equilibrium of forces in the horizontal direction. Refer to the free body diagram of the reaction forces for the horizontal forces. The only horizontal force is HA at point A. Since HA is the only horizontal force, the equilibrium equation can be expressed as follows. We will now analyze the rotational equilibrium of moments. First, examine the lines of action for all forces. The lines of action are as follows. The line of action for VA. The line of action for HA. The line of action for P1. The line of action for P2. The line of action for P3. To determine the magnitude and direction of the moment caused by a translational force, it is necessary to have information about the arm length relative to the center of rotation, which is calculated from the force's line of action. In contrast, the reaction moment ma in the figure already has the defined magnitude of ma and the counterclockwise direction. Therefore, the concepts of line of action and arm length are not necessary for the moment. Next, select the center of rotation. Choosing the point through which as many lines of action of the unknown reaction forces pass as possible will simplify the calculations for determining these reaction forces. In this case, we will select point A, through which the lines of action of the unknown forces, VA and H pass, as the center of rotation. Then, calculate the shortest distance, from each line of action, to the center of rotation at point A. This shortest distance will serve as the moment arm length for each force, relative to the center of rotation. Since the line of action for the force VA passes through point A, the arm length is 0. Similarly, the line of action for the force HA also passes through point A, so its arm length is 0. The arm length for the force P1 is 1/3 of L. The arm length for the force P2 is 2/3 of L. The arm length for the force P3 is L. We will derive the equilibrium equation for these moments. In the summation of moments, clockwise moments are considered positive. The center of rotation is point A. Let's clarify this. Since the arm length of VA, with respect to the center of rotation, is 0, its contribution is 0. Similarly, since the arm length of HA, with respect to the center of rotation, is 0, its contribution is 0. The reaction moment MA acts counterclockwise, so it contributes -MA. The action force P1 acts clockwise, so it contributes plus P1 multiplied by 1/3 of L. The action force P2 acts clockwise, so it contributes plus P2 multiplied by 2/3 of L. The action force P3 acts clockwise, so it contributes plus P3 multiplied by L. To achieve equilibrium of moments, the algebraic sum must be 0. This concludes the discussion on rotational equilibrium. The reaction forces, VA, HA, and MA, are determined through the equilibrium of forces in 3 directions, as follows. The signs of these forces are based on the free body diagram shown on the left. The positive sign of VA indicates that this reaction force acts upward, which is consistent with the vector assumed in the free body diagram. Since HA is 0, there is no direction associated with it. The positive sign of MA indicates that this reaction moment acts counterclockwise, which is consistent with the vector assumed in the free body diagram.